Jim said what Rafi and I are doing this morning is a little bit of a two-step sort of dance explaining some of the science that's going into supporting the combined biostimulatory and biointegrity policy today. Okay, so Jessie had a lot of sort of points that she covered, but I think that sort of main take-home message for you guys with respect to the instructions to the science team in terms of what is the science that we're developing to support this policy really is sort of two pieces. The first thing is that we need some basis for how we're going to be establishing the endpoints or goals for aquatic life use. What's the science that would support that? And in order to be able to really drive and put teeth on decisions that go into a number of different aspects of the water board programs and how we employ them. And then the second piece is being able to come up with these biostimulatory objectives. And so what we want to be able to do today is talk a little bit about what does this mean with respect to the tools that we want to bring to the table to give you enough background that you have a sense of where you can go to explore more about these tools on the water board. And if you want to get involved or talk with us about it, then we're happy to hear your questions. So, the way we want to divvy up the talk between Rafi and I is that they're essentially, between the biointegrity, that's Rafi, and the biostimulatory, that's me, we're going to be sort of dividing up the talk. And the first three components of these tools that are being developed are really more about biointegrity. So Rafi's going to cover those first. And then I'll come back and I'll talk to you about what we're doing to really support the water board programs through the biostimulatory component. So I'm going to bring up Rafi here now and let him take it away.
Thank you. So I'm going to talk about a number of sort of technical developments that we've done to help support the assessment of biological integrity and the interpretation of biological integrity. There's three components that I'm talking about. One is our scoring tools, our assessment indices. That is, how do you take biological data and turn it into a measure of condition? And that's involving the indices you've already heard about a lot today, the CSCI and the algae equivalent. Second, I'm going to talk about how we interpret those scores and what they mean, and that has to do with what we've been referring to as the biological condition gradient modeling. And finally, I'm going to talk about some modeling efforts that we've done to help put your scores in an environmental context so you know how your site's doing relative to how sites in similar conditions perform. I won't be talking about our physical habitat index. You'll hear Andy talk about that after lunch, and it's certainly related to this policy, so definitely stay tuned for that. So our scoring tools, they are a standardized way of interpreting biological taxonomic data. When we developed them, we had this goal of having a consistent statewide tool that will work in pretty much any perennial or any wadable stream in California, perennial and even some intermittent streams. The CSCI, it's been available since 2016, and as you heard from Jessie, it's already being used in a variety of programs such as the Integrated Report. Right now we've been developing the algae stream condition index, and by we, I really mean my coworker Susie Thoreau, who is with her first child now, so she can't be with us today. But this index, we have provisional indices available now that we're having our advisory groups review and provide us with feedback, and that'll be finalized over the next few months. So if you're familiar with the CSCI, this is a bit of a review, but the ASCI, the ASCII, it's being designed to have a very similar approach towards assessing condition as the CSCI. We're looking at two different ways of assessing condition. One, we're trying to see, are all the taxa you expect to find observed? That is, do you have all your observed to expected taxa? You look at the ratio of O to E. And the other component is you're looking at biological metrics. So you're looking more like what they're doing. So do you have all of your motile taxa or your nitrogen fixing taxa? So it's a bit of who's there and what are they doing, and are those both matching your expectations for that site? algae is a little bit more complicated than bugs. For starters, we're looking at two pretty different assemblages. We're looking at diatoms as well as soft-bodied algae. That's SBA is soft-bodied. And so we're exploring different ways of developing an index, whether you're looking at the diatoms, soft-bodied algae, or both together. This is actually following the work that Betty had done in Southern California, Betty Fetcher. And we're looking at multiple taxonomic resolutions. And what we're finding so far, just to sort of cut to the chase, we found that for our O to E indices, the genus level models performed quite a bit better than our species level O to E models. So it seems likely that whatever index we end up using will include genus level O to E index, not species level. But when I say that the performance is better, it was still, I would say, kind of mediocre. We're trying to fine-tune these models and see if we can improve the precision and sensitivity of these indices further with additional refinements. When we look at our multi-metric indices, we actually find that performance is quite a bit better. They all had much better precision and sensitivity than the O to E model. So right now, the choice that we're facing is whether we want to include which flavor of the MMIs and which flavors of the ODs, if any. We might not end up using one of each. Those are questions that we're exploring right now. When I tell you that the performance was good or bad, this is kind of the stuff that we look at. These are scores from reference sites from throughout the state. Each box plot represents a different region of the state. It's the PSA regions that Calvin had mentioned earlier. And what we're looking for is that there's not a lot of variation among regions, and they tend to be all consistently over that line. And with the possible exception of the Central Valley, where we only have 2 reference sites, most of these scores are pretty consistent above that line. When we look at sensitivity or responsiveness, what we want to see is that our reference sites have quite a bit higher scores than what you find at our high activity or our stressed sites. And so you want to see a big difference between these green and orange boxes and these box plots. And on this factor, you can see how the O to E indices are not quite as strong as the MMIs. So that's not really a lot of detail about these indices, and that's because a lot of this you can actually look at for yourself. We've put together this website, which if you don't have time to write this down, I know that Jim makes all of these slides available to you guys after the conference, so you can get that way. And we have these websites that help you really explore the methods and the development data that we used, as well as look at some of the results. You can make some interactive graphics to see how that score represents to different stressors or natural factors that might interest you. And if you're not part of the advisory groups that are participating in the Biointegrity-Biostimulatory policy, this is probably a really good way for you to provide feedback to us on these tools, ask questions, and just let us know where you think it might be working well or not working well. So I'm going to shift gears now and talk about our biological condition gradient models. And so we have these 2 indices, the CSCI and the ASCI, and these are really good tools for measuring biological condition along a gradient. As the scores decrease, we know that the biological condition is presumed to deteriorate in terms of the structure, ecosystem structure, and function. But we don't really have an easy way to set benchmarks to know where function has been profoundly altered from natural conditions. And this is sort of what the BCG approach attempts to do, the biological condition grading approach. What this approach does is it takes your sort of platonic ideal of streams and defines what are the types of functions and structures, and you assess how it deteriorates as stressors increase. And we're using these standard states or bins of condition along that gradient that have been developed for the entire US, these 6 different states. And we had a panel of experts assembled for California to really define what those meant for California. And I just want to point out that a number of these experts are actually in this room today, and so I appreciate if you guys could wave your hands so everyone can see you and ask you questions about it. We got John, Jeanette, Andy, Tina, Allison, quite a few, Bill. So a number of you guys, this group was really the source of expertise for deriving these models. Ultimately, what we're doing is we're taking these expert panel opinion, expert assessments of function and structure and trying to link it to your CSCR ASCII scores so you really have a better understanding when you know your score, what do expert stream ecologists think that means about the function structure of that stream. Briefly, these are the 6 bins that the EPA has defined, ranging from natural or pristine condition to severe changes in structure and a major loss of function. I'd argue that there's actually a 7th bin there that says that the stream no longer supports aquatic life. 6 is not the worst you could possibly do, but that's not the standard definition, so I didn't put it on there. We asked our panel, we gave our panel quite a lot of data to work with, 250 sites worth of data. We gave them taxonomic information. For bugs and algae, we had 2 panels, one focused on bugs, the other focused on algae. We calculated some of the assessment metrics, and we also gave them quite a bit of environmental information, things like elevation, geography, climate, but no stressor data. So they had no information on whether or not a site was disturbed or affected by human activity. And they assigned sites to one of these 6 classes based on that taxonomic data. And you end up with a graph that looks kind of like this, which I actually thought was quite good, quite a bit better than I was expecting. You see CSCI scores decline along those bins in almost a monotonic fashion. And this gives you a nice way to help interpret, given a certain score, what would this panel of experts, what bin would they put that in? And you can also look at that 0.79 threshold, which has been mentioned earlier today. You can see how that really seems to separate that bin 3 and bin 4. And that really helps you talk about, if you're going to use that 0.79 as a threshold, this really gives you a new vocabulary for talking about what it is you're trying to protect with that bin. And I'm not going to sort of go through too much of this today, but it basically talks about what are the structures and functions that are perhaps altered when you're looking at bin 3 or better. So what can you do with this? Again, the primary goal for this effort was to help the water board make decisions about setting thresholds. So really the primary aim is to help you interpret those thresholds. So you can now talk about what a threshold of 0.79 might mean in this sort of narrative of structure and function. But outside of just threshold setting, it really is a valuable communication tool. You can now talk about what your goals are for restoration in a slightly more meaningful way. This last line is something that P. Odie said, that when you start talking about these things in terms of structure and function, you're really refocusing on the real objective of our stream management. It's not to raise your CSCI scores, it's to restore lost structure and function. Okay, what can't you do with this? There are a number of things I would say can be easily misinterpreted about applications of this model. The BCG is not a substitute for an index. It doesn't give you a way to look at taxonomic data and infer what the condition is. You need your index to do that. It doesn't tell you anything about the limits or why it's in poor condition. So, if you have a site that you determine is in what I call bin 5, that doesn't mean you can't score better or that you can't alter the management somehow to improve conditions there. And finally, it doesn't tell you anything about the causes of impairment. You're not going to know whether it's water quality, habitat, or something else causing that score to be low. So the third element I want to talk to you about is some landscape modeling that we're doing to try to give you context for assessing ranges of conditions you'd expect in different watersheds. And so the impetus for this work really came from some of the major struggles that we encountered in the first round of bioobjective development, is that we knew that there were all these streams out there where we didn't think it was likely that you could achieve high scores, but we didn't have a clear way to go about identifying which streams they were. So I'm showing here some results from the SMC's annual report last year. The SMC classified sites as being hardened or engineered in earthen or natural, and it's pretty clear from that box plot on the left that in your hardened channels, you pretty much never observe high CSCI scores. You never get above that threshold of 0.79. And if you look at the problem in a slightly different way, instead of looking at channel structure, you look at landscape activity, like land cover, you see the same pattern that at high levels of alteration, you don't really see high scores. So it really seems that these high scores might be precluded in those types of settings. Perhaps a bit more concerning is the fact that within these types of systems, you have a pretty dampened response to water quality gradients, and I would draw your attention mostly to the one on the right. The red line represents natural channels, and you see a really steep decline as conductivity goes up, scores go down. This is consistent with something that Calvin showed us with the urban channels on his map. But when you look at the hardened channels, that blue line, you see there's almost no response. And so the punchline is that a lot of the things that we might do to improve water quality, they might not work to do much to protect biological integrity in these types of systems. So clearly you need a new and different kind of conversation about how to manage these streams. So we're taking a landscape approach to predicting biological integrity for streams based on the types of landscapes that they're in. And this is really jumping off of work that Ryan Hill from the EPA pioneered, doing a nationwide analysis, but here we're trying to adapt it to work for California and adapt it to our regulatory needs. What we're trying to do is develop ways to rapidly screen sites and identify those where you think high scores could be attainable and those where you think they'd be unlikely to be attained. And that helps you prioritize different types of management activities. And like I said, these are all screening tools or conversation starters, not jurisdictional tools. The approach we're using takes advantage of the StreamCAD dataset. This is what Ryan developed for his efforts. Basically, the StreamCAD database is a database of GIS metrics calculated for every stream segment in the National Hydrography dataset. If you aren't familiar with this, I highly suggest you download and play with it. There's a lot you can do with this tool. It's pretty cool. For each stream segment, there's hundreds of variables you could choose from. We focus on those relating to anthropogenic activities, things like land cover, road density, dams and mines. But there's also a lot of natural data you could look at, like geology, climate, etc. And so we used all the data we had in California from our bioassessment programs. This is over 3,000 sites that we used to develop the model. Because of StreamCAD, we had the GIS metrics calculated already for pretty much every site. And we were able to develop models that we thought were actually pretty darn good. On the left, you can see how the predicted and observed CSCI scores compare, and it's not a bad R-squared. And then you can see that when you look across the different regions of the state, there's not really a clear bias where there's one region where it's scoring much higher or lower from its expected. So you have these models, how do you use them? And I'm just going to illustrate one example, one potential approach for using these models to create a classification scheme. I'm looking at three different classes of streams. You have what I'm calling likely high scoring streams. These are streams where the predicted range of scores is all pretty high, and I'm saying that you have a low chance of scoring below 0.79. So I'm making two sort of somewhat arbitrary decisions. 10% is what I consider to be a low chance. 0.79 is what I consider to be high scoring. The other side of the spectrum, you have what I'm calling likely constrained streams. These have a low chance of scoring above 0.79. That leaves a whole bunch of streams in this intermediate category, and these can be intermediate because you're pretty sure that it's going to score really close to that 0.79 threshold, or it could be you have a really wide range of scores. You're not really sure what it's going to score, and you probably have both situations going on depending on which types of sites you're in. Finally, there's a number of streams where I actually didn't have the data I needed to make the classification. So these are what I'll call these not determined. And so these color schemes, dark blue, light blue, red, and yellow, this is what the state of California looks like. And it's not actually all that surprising. You got a lot of likely high quality streams throughout the Sierra Nevada mountains and Northern California and the Big Sur area, as well as the higher elevations of Southern California. The constrained streams are mostly located in the urban areas of Southern California, the Bay Area, as well as the Central Valley Sierra foothills, but they only comprise 6% of the stream miles in the state. There's a lot, about a quarter of the stream miles are, we didn't have the data in StreamCAD for modeling. Now in some cases, like in the Mojave Desert, these are likely undisturbed high quality streams where we just don't have the right information. In the Central Valley, it's probably a different story. But right now we're just exploring a number of approaches that we could use for dealing with these systems that might not depend so heavily on the StreamCAD data set. So the real goal here is to really start helping people talk about what they want to do with these different types of streams. So, like I said, we're trying to inform management priorities. And so what I have here is just 12 example sites. The bars represent the ranges of predicted scores, and the dots represent the observed score. So there's 12 different possible scenarios that you could experience relative to that range and a standard threshold. One application would be you want to prioritize sites you want to fix, and this could be either by doing a TMDL or some kind of causal assessment or any kind of intervention. So you want to prioritize different activities, and what I'm showing you here are some of the priorities that were discussed in our work group advisory groups. They don't necessarily reflect any water board policies at this time, but you can see I just want to contrast. Here you have a fairly low scoring site that's scoring well within the range of predicted scores, and you have one that's below that range. And you could argue that this one should be prioritized over this one because this one is probably can be improved much, whereas this one, that's scoring exactly what you'd expect for a similarly urbanized site. There are, of course, other activities you could talk about. You might want to prioritize different sites for follow-up monitoring. And in general, people wanted to focus on sites that were either greatly underperforming or overperforming relative to its predicted score. And of course, you might want to prioritize different streams for different types of protection. And not only do you want to necessarily focus on your high-scoring sites over here, but maybe even some low-scoring sites that are still doing a lot better than you'd expect for that type of setting. So these are 3 different elements that are going to be used for both the state board's Biointegrity-Biostimulatory plan as well as San Diego's biological objectives in some capacity or another. And with that, I'm going to hand it over to Martha to talk about biostimulatory linkages.
Okay, thanks, Rafi. So as Rafi said, so what's happened then is that we have these tools that are centered around biointegrity and assisting the state not only with a new method, so a new index, the ASCII, but coming up with ways to support decisions and conversations about what expectations to set on streams with respect to biointegrity. So now what we're going to do is we're going to move over and talk about biostimulatory. And so you can think about biostimulatory as a major class of stressors to stream. And what Jesse said was, well, the Water Board wants to set a policy for biostimulatory, likely based on a narrative objective, but with a numeric translator. And so for most people, what you hear when you see something like that is that, okay, they want to set numeric nutrient endpoints. And in fact, the old version of the biostimulatory policy used to be called the NNE, nutrient numeric endpoint, because of this focus on nutrients. But I think it's really helpful for us to take a big step back and actually say, well, what is biostimulatory? And actually, if you go into each and every one of the Water Board's basin plans, the regional board's basin plans, you see this thing called a narrative biostimulatory objective. And it says something like, thou shalt not create algal nuisance problems, blah, 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 right? So what is that really? And so what happens is that biostimulatory conditions create a problem called eutrophication. You maybe heard that word this morning. And eutrophication is defined as the accelerated accumulation of organic matter. Yes, caused by algae or aquatic plants and the overgrowth. And we tend to really think of this as mostly a nitrogen and phosphorus problem, and indeed it is. But the other things that happen when you urbanize landscapes or you develop landscapes really are part and parcel of that same biostimulatory problem. Hydromod, light, so if you put a channel into concrete, you're having a lot more light, you create conditions, much warmer temperatures, physical habitat alteration, as well as oftentimes what happens is sometimes upstream you have just a dumping of organic matter that can come in from scouring a eutrophic habitat upstream, or there's a legacy organic matter. And all of these factors roll into what we call sort of collectively biostimulatory conditions. And this is what the policy is intended to prevent. And what we're really doing is we're preventing that problem called eutrophication. So then how do we think about this? And so what I've shown here, and it looks like this pointer isn't working, but if you go all the way over to the left-hand side of the screen, you see of biostimulatory conditions and this excessive algal mats that are produced, for example, and what I've designated as OM, or organic matter. And they cause a number of different problems for aquatic life. They smother the habitat, they cause wildly swinging DO and pH, and they draw down the dissolved oxygen to the point where you start to have some big impacts to fish and other aquatic life. And you also have direct effects, for example, ammonia toxicity. You also have problems with toxic cyanobacteria. All of these can impact aquatic life. So this is really what a lot of you folks are focused on. And Jesse mentioned that the Water Board wants to decide whether or not they're going to have parts of this policy also touch on human health impacts. And there are some, with respect to the designated uses that the Water Board is supposed to be protecting. For example, reduced aesthetics impact to REC 2, and as well as REC 1 or municipal drinking water impacts from those toxic blooms, as well as just degraded water quality. Okay, so each of these sort of pathways of impact become the way in which we start to think about how do we measure the problem. What does a problem look like when you have a problem, and how do we measure it? And so each of these pathways shows you essentially groups of metrics that we would measure if you're diagnosing eutrophication. So at the very top you have the CSCI and ASCI indices, and their index component metrics can be used to diagnose whether or not you're impacting aquatic life. This benthochlorophyll and ash-free dry mass are bulk measures of organic matter availability, so if you have a lot of it, that's not good. Percent cover is sort of a way that you can assess whether or not visually it's looking kind of gnarly, for example. Cytotoxins and DO and pH are sort of given. Okay. And so what happens is if we have these sort of standard measures for how we assess eutrophication, then what we really need to be able to do is come up with ways of actually picking numbers for them. And so a lot of the work that we're doing is in terms of that handoff, and even the chicken of the egg that Jesse talked about this morning, is really understanding how do we develop the key graphics to help the Water Board choose numbers in terms of protecting high quality habitat, as well as diagnosing when something is impaired. Okay, so what's the basis for these numeric targets then? So first of all, what's really helpful to understand is that what I have in sort of this category of response indicators becomes a way in which we can try to use those indicators as multiple lines of evidence to diagnose whether or not you have a eutrophication problem versus some other problem that may be impacting aquatic life. So, we would be assessing, we would look at the index component metrics. Are there certain metrics within those indices that are actually telling us more information about what's being impacted and by what pathway? We would look at the organic matter, the cyanotoxins, as well as the DO and pH. And so we want to be able to set eutrophication targets based on those response indicators to know whether or not we have a eutrophication problem. And luckily for things like DO and pH and cyanotoxins, there exists guidance, either statewide or federal, for example, that point to the numbers that we should be using. And so really what it comes down to is for that set of bulk organic matter measures like benthochlorophyll and ash-free dry mass, then we need to be able to come up with targets. And it turns out that one way of doing that is essentially relating that back to the CSCI and ASCI indices. And then finally, because ultimately what we want to be able to do is prevent the conditions that are causing eutrophication, we also want to relate it back to nitrogen and phosphorus. And so ultimately what we're going to be doing then is utilizing this great statewide bioassessment data set as a way of defining some screening level targets at a statewide scale. And then again, Jesse set the stage for this idea that you set these sort of screening level targets, but then also potentially allow some flexibility to think about how do you manage biostimulatory conditions at a watershed scale. Okay, so whereas a lot of the work that has been done on the biointegrity tools that Rafi has talked about, they're really almost at their completion. We're nearing the end of that work because of the need to kind of slow down and really work with the Water Board on policy options. The modeling, the statistical modeling that we're doing to have conversations about what's the basis for those biostimulatory targets is really just getting started, and you're going to see this work happening over the next year. And so what I'm showing you basically is just an example of some of the graphics that we can produce, the key graphics that we can produce that start to support conversations around what those numbers should be. And there's no modeling done here. This is just a distribution of total nitrogen on the bottom axis versus CSCI on the y-axis. But it shows you what some of the potential targets are for this CSCI and sort of imagine how you could start to draw lines and relate that back to total nitrogen concentration. And for what it's worth, you know, when you look at these numbers, what we already know is, oh wow, they're actually going to be pretty low. And so if you think about typical wastewater treatment, the effluent from wastewater treatment or from ag runoff, we're usually in the tens of milligrams per liters, maybe as low as 5 milligrams per liter, where a lot of the action that we're seeing in terms of the decline of the CSCI score, and the same thing with the ASCI, is really at or around 1 milligram per liter or lower. So the bottom line is that even though we have a lot of modeling approaches that we could use to draw these lines, what we're probably going to do is end up prioritizing a simple modeling approach for a statewide application, knowing that when you get to the point where you're really above 1, you're going to start to need to have a more difficult conversation about how do you manage and how do you set limits, especially for ag and wastewater treatment, which is where really where the rubber is going to hit the road. Okay, and so I said then, just to be clear, is that we want to be able to set targets not only for the biostimulatory conditions, total nitrogen, as well as total phosphorus, but also the response indicators that are specific for eutrophication, so benthic chlorophyll A and ash-free dry mass, and then related not only to the CSCI, but the other new index that we're in the process of developing, which is the ASCI. And so together, these will represent a set of numeric ranges on the x-axis for biostimulatory and indicators that are diagnostic of eutrophication that the Water Board can be considering in advice with, you know, all the different advisor groups, what numbers they want to choose to actually set those statewide targets if they choose to do that. Okay, so we said, all right, yes, statewide targets, but then there's this thing called the, what did you call it, Jesse? Watershed, coordinated watershed approach. So what is that, and why would you want to do that? Well, the idea is that ultimately, if you're actually starting to talk about managing nutrients or any other biostimulatory conditions, you really need to think about a watershed approach, because there are a lot of factors that can make that a complicated proposition. And so when is that called for? Well, number one, you know, Rafi gave you an example of some models that you can use to identify places where the landscape development may be constraining biological integrity. So, you know, this is not likely to be necessary in a place that's already meeting reference conditions. So this is a place where you have some complicating factors, and complex decisions are required in order to manage those places. Sometimes you have multiple and sometimes competing aquatic life and human uses. For example, if you are trying to manage recycled water, but the recycled water has high nutrients, what do you do about that? So this is a good sort of place where you're going to want to think about a watershed approach. And then finally, it's really important to have an engaged stakeholder group who's are willing to invest the time and the money and the energy in the data and the models to refine the science, because that's really what's required. Okay, so then what is it that you can do with this watershed approach? What's sort of ideal then is that you can start a little bit higher up and think about, well, what are your aquatic life use goals? What are your human health goals? Do a causal assessment, because it won't be just about biostimulatory, I can guarantee it. But if your causal assessment points in part to this idea of having the need for management of biostimulatory conditions, then you can really employ a combination of statistical and mechanistic models to look at not only nutrient management, but also flow management as well as habitat restoration as a way of solving the problem. Sometimes it's not a nutrient problem, sometimes it's really about restoration. And so that really becomes some great opportunities for us to think about how do we repair the watershed, or at least mitigate the problems more holistically. It also allows you to consider some of the impacts on the downstream sensitive habitats which is really hard to do when you're kind of coming up with statewide statistical models. And so finally, the other thing is that you're able to really pull in some of your indicators that may point to things that really speak to people, like dissolved oxygen and salmonids, for example. Okay, so the idea is that somehow we're developing this toolkit that allows you to start to walk into conversations about where in the landscape you need to be able to manage biointegrity, and then how do you kind of pick off one of the large class of stressors, which is biostimulatory. Okay, so quickly then, just because I see that Jim's standing up over there, next steps and timing of science projects, products. So I said that Rafi and the team, the biointegrity team, have really been pushing and getting all the biointegrity tools together. We're almost at the point, you're already seeing some of them hit the streets. So all of them will be ready for draft review by early spring 2018. Jesse said that the upper management is being engaged around policy options, so we'll be doing statistical modeling around those policy options for biostimulatory, and we're expecting to have the draft products for public review by the fall of 2018. And the thing that we didn't really talk a lot about, but I really want to emphasize the need for case studies. So, how do you use those tools in hard to manage places? And so we have two good examples. One is the Santa Margarita River watershed, in which the focus is nutrient management, and the San Gabriel River watershed, in which they're sort of employing the channels and developed landscapes models to support conversations about restoration. And so those watershed pilots are really great examples of how to use those tools, and I would encourage you guys to follow up with us if you're interested, or if you have a watershed that you'd like to try these ideas out on.